Okay, so hi everyone, welcome to the 86th session of the MedAI Group Exchange Sessions. This week we have Yoon Liu from Google Research here to speak about all their work on health AI from both development to deployment. And Yoon is a staff research scientist at Google Research, and he focuses on developing and validating ML for healthcare across a variety of fields, including pathology, ophthalmology, radiology, dermatology, and more. He completed his PhD at Harvard MIT Health Sciences and Technology, and he worked a lot on predictive risk modeling using different biomedical signals, as well as medical text and billing codes. So he's also worked on nucleic acid sequences and protein structures, and he completed a BS in molecular and cellular biology and CS in Johns Hopkins. So thanks so much, Yoon, for joining us today. And I guess before we start, do you have any preferences on how you'd like to take questions? Is it okay if we interrupt you, or do you have like dedicated times where you'd like us to ask questions?
Yeah, definitely feel free to jump in with questions. I'm using a web version, so I apologize in advance if I don't see kind of like people waving, but I think if you ping something in chat, I can switch over and take a look.
Okay, cool. Yeah, I guess Amara and I can also just keep an eye out on the chat and let you know if we have like questions there. But yeah, without further ado, let me hand it over to you for his talk.
Sounds good. Thank you everyone for joining. I'm gonna pull up the slides right now. And in particular, thanks for jumping on a different timing than your usual weekly. So are my slides showing up?
Yes.
Great. So today I'm going to talk about some of our work in the health AI space, starting from kind of like the code and going all the way to the clinic and some of the lessons that we learned. And so that will be, I think, a big part of the talk. And then closer to the end of the talk, I'll talk more about some of our vision for how do we learn more from machine learning models than purely focusing on predictive modeling. And this is representing the work done by many people, and it's been my pleasure to share some of this stuff with you. So the work that our group focuses on spans a lot of different fields, ranging from imaging, including radiology, pathology, ophthalmology, and dermatology, to things more recent in the generative AI space involving language models and explainability. And I'll talk about explainability in this talk, but I'll mostly skip over the language model stuff. If you're interested in that work, look for one of the MedAI talks recently by my colleague Vivek, where he talks about our MedPalm work as well as some of the foundation model work. So the first part of our talk really focuses on how do we build AI models and some of the lessons that we've learned in terms of the broad strokes. So I won't be going into detail about any specific individual paper, but really trying to cover a broad range of papers and the lessons that we learned that were common to multiple studies. So 3 of the myths that we found in terms of thinking about developing health AI models. Number 1 is get more data, and that's all you need. Number 2 is once you have a good model, that's all you need for a good product. And number 3 is that a good product will lead towards clinical impact. And so there's a lot more nuance to these 3 concepts, and I'll share more. So first one, well, if you have more data, that's generally a good thing, but there's some nuance in terms of data quality. And so before we dive deep into that, let's just very quickly recap when we talk about machine learning models nowadays, how they're trained. And this is a sort of like a cartoon version of this, where essentially training some of these models now just involves showing many examples of these models to a neural network, and then back propagating essentially if it got it wrong or right into the network, and then modifying the weights such as more likely to get it right the next time. And by doing this over millions of cycles, it tends to start learning useful stuff in these connections and allows you to then do classification or other tasks based on a new input example. So in this particular example, one of the running examples I'll be using is this example on diabetic eye disease, or DR. And in this example, what we did was the input photos are these fundus photos. These are photos of the back of the eye. So this is where the retina is. And you're looking at the optic disc, that's the little bright spot here. Here are blood vessels, and the middle part, that's the fovea. That's where you're getting most of your high fidelity vision. So what we did in this work was that we labeled a number of images, and we used an off-the-shelf algorithm at that time. So this architecture was Inception. I believe this was V3, and it was used to predict a 5-point DR scale ranging from no to proliferative, as well as some auxiliary labels based on left and right eye, field of view, and such. That was more sort of like useful for products than for the core prediction. And when we did that and we did some ablation analysis, what we found in terms of data volume is something that's not surprising to many of us sitting here today, where the more data, the better, and performance does improve with the amount of data they are providing, except that it starts to plateau after a certain amount of time. Now, depending on the kind of application that you are in, you might see that you are in the steeply increasing area where if you just get a bit more data, it's going to improve the performance by quite a bit. Or you might see that you're in the more plateau area, and if you are, congratulations, that's a really good spot to be. But this is a little bit, this is only part of the picture. And so to illustrate why, let me go back to this slide and highlight a couple of the numbers here. One number here is the number of images we had, so a bit over 100,000. And the second is the number of labels we got for these images, and it's 800,000. So clearly, we got more labels than one label per image. And why is that? So here's a chart of some of the early labeling that we did and what we found. Every row here is a single image. Every column here are labels by different graders. And what we found here, and what we really want to see here, is that every row is a uniform color, meaning, let's say, for example, this image should be all blue, meaning everyone thought there was no DR in there. And indeed, we see that for a few of the rows. For example, these last two rows, we saw that everyone labeled it as proliferative DR. But if we look at two of these highlighted rows here, we see that essentially there's like at least one person grading it as one of every single one of these 5 colors. And so that's unfortunate because it means that we don't know what the ground truth should be when we're training and evaluating the models. So to get around it, in that first piece of work, the way we did that was to get multiple labels and take the majority vote. So we know that majority of graders would have considered any given image a particular grade. So that's how we were training it. Now in that setup, let's think about what happens if we got fewer labels per image. And so let's take a look at when we develop a model, we usually have a data set we're using for training and a data set we use for tuning. And this is often called a validation set in the machine learning world. In the clinical world, we call it a tune set, mostly because there's a concept called clinical validation. And so we didn't want to reduce overloading of the term validation. But in many circles, you would call this a validation set. And let's look at what happens when we reduce the amount of labels that we get for the train set versus for the tune set. And so this is what we saw. When we started from roughly, say, about 4 labels per data point, and then we decrease it for the training set, at the level of data that we started with, this didn't really impact the model performance. However, when we do the same thing for the tune set, that had a dramatic impact on the model performance. And the tune set here is being used to select model checkpoints, determine hyperparameters, and other things. And so what the takeaway of this slide is that if you had the budget to go label more examples, at some point you might be much better off labeling more of the tune or validation set because that helps you make better decisions about what model you are selecting. So far what we've talked about was really if you have the budget to go label more stuff, and if you get multiple reads and you take the majority, it tends to be a little bit better than if you were to take just single reads because it gives you a less noisy measurement of what the ground truth is. Now, another thing that's a bit of a nuance here is that if you have multiple reads per example, it is possible that the majority is actually wrong, but the minority is correct. And we've seen this sort of like concept actually across multiple different studies for ophthalmology, dermatology, radiology, and this was pathology. And so how do we resolve that? Well, one thing you can do here is to do something called arbitration or adjudication, where instead of just taking a majority, you actually you get the graders to talk to each other and determine who is correct. And the way that we tend to do adjudication is we do something called asynchronous adjudication. And what this means is that instead of actually getting people physically or virtually in the same room at the same time, we actually have graders that say A, B, and C, each individually review the images, provide their grade and their reasoning, and then if there's no agreement, then individually it goes back to each of them along with the anonymized comments and grades from the previous graders. And what this does is that it reduces the phenomenon, that's something like the loudest voice in the room, where if there's a more senior person saying that it's something, the more junior people may be much less likely to disagree with them. So we found that asynchronous adjudication lets us get around that. And another benefit is because it's asynchronous, we can actually get a more diverse pool of graders from around the world as opposed to getting people that's all in the same time zone or department. So when we apply this concept of asynchronous adjudication to the ophthalmology space for the same DR model we've been discussing, we found that the model performance improved quite a bit from being on par with general ophthalmologists, general eye doctors, to being on par with retina specialists. So we've talked about label noise, getting more labels, and what do you do with it during training and during tuning. Another part of this is that beyond training and tuning, it can also impact evaluation. So let's take a look at a toy example here. So here,
I actually have a question. I don't know if you want to take that question like after this section or before. I was thinking that like some of the images where you have such a variance in labels from different experts, could that be a signal of like the complexity of the retina? Like maybe that's like a harder example for the model. So could there could there be one more case instead of having 5 grades, like an uncertainty or like complication, like level of complication kind of a thing that you can get signal from instead of making the labels really good is of course a great thing, but like from a first pass, you can also kind of like try to inject some uncertainty modeling into your model based on this disagreement. Just wanted to get your thoughts on.
Yeah, definitely. I think that that's definitely true, and to some extent, when we train models, I think it's much more common to use soft labels nowadays, even for classification problems, than using hard labels. So I think that there's definitely some amount of that happening, irrespective of what the labeling actually looks like. So completely agreed. In terms of injecting uncertainty, I think that helps. Where it becomes more difficult to do, I think, is during evaluation, because you really want to, figure out how to evaluate it, right? Because you can train it with some of uncertainty or confidence, or telling it here's a distribution of the ground truth. But when you do the evaluation, like, how do you know when it's right if there's some uncertainty? And I'll cover that in just a second. But hopefully that covers.
Yeah, and just maybe like piggybacking on that question, were there some like things that people found when they were discussing like why a case was like maybe having such a wide variance versus not? Like, was there some amount of like it being straightforward versus like more subtle signals or something?
Yeah, so I think that there's probably many ways to characterize uncertainty or ambiguity, and there's some technical terms here. But I think broadly, qualitatively, I would think about it as one being something more of a detection disagreement, and one being more of a classification disagreement, where the former refers to something where they just didn't notice something, right? So if you were to point them out, like, hey, I think this was mild because I saw this microaneurysm at this corner, right? Once that's pointed out, everyone goes like, oh yeah, you're right. No argument there. When it becomes more of a classification uncertainty is when everyone's looking at the same thing but disagreeing about what the thing that they're looking at is. And occasionally that resolves if you have, let's say, in the dermatology space, we have this phenomenon where sometimes people look at just the photograph and they disagree about what it is. But if we give them more metadata, for example, this person has a history of eczema, right? Now that changes things, because you know that you have a much higher prior for a certain diagnosis, or you say that, hey, they are actually 70 years old. And in that situation, you go like, well, actually this other diagnosis is very unlikely in a 70-year-old individual, so it's much more likely this other thing. So I think sometimes the metadata helps, but sometimes you do still have some amount of disagreement that's just not resolvable without doing additional testing and other things that you often don't have.
Cool. Yeah, thank you.
Great.
And if in your experiment about labels per image for the training and the tune set, did you notice any variation in the performance based on how large your tune set is? I mean, I think it's standard to get like 20% as tune set, but any thoughts on if we make it like maybe very small, 5%, or maybe very large, let's say like maybe 40-50% of your test set? It's not ideal, I understand, like you need data for training, but any relation between the size of the tune set and the performance?
Yeah, so I think it's definitely a challenge if you have a kind of like a static data set size that you can divide into training, tuning, or training validation, or train, tune, and test. How do you do that division? And I think really the way I try to approach this is, what is the absolute number that you need to have some confidence in the numbers that you're looking at, right? So for example, you're using, let's say, AROC for the validation set sort of evaluation. And what you can do is compute the confidence intervals around that, right? So if let's say there's 5 examples, the confidence intervals are, I don't know, let's say 40% wide, right? At that point, you have no confidence in the numbers that you're seeing, right? And so you need to make it much smaller. And so, just as a rough gauge, like usually I try to have at least 1,000 examples, assuming there's not severe class imbalance in the tune and validation set, just so I have a rough confidence that those numbers are meaningful. And if that ends up being 5% versus 20%, I think depends on the situation that you're in. But if it's if 50% ends up being like 20 examples, then you have an overall data set limitation problem, and you have to resolve that separately. Beyond the just triggering with the ratio.
Thank you.
Great. Okay, so in terms of label noise and evaluation, in this toy example, you have 10 examples, and you have 2 colors. So this is a 2-class problem, and this is the AI prediction. So let's see what happens if you had a bunch of graders grade those same cases, and they have a concordance between the 3 graders of about 70% if you just look at pairwise concordances. When you have that and you evaluate the AI model that you have against each of these graders individually, you're going to get this particular set of accuracy metrics, 70, 40, and 100, which is a very large spread in the accuracy numbers. Now, this is a toy example, but let's say in this toy example, instead of having graders, you now have panels that grade each image. And let's say the panels have a higher concordance between them of about 80%. This will now result in a smaller spread of uncertainty between the metrics that you're computing, ranging from 50 to 90%. And let's say instead of doing that, you get something that's even more reliable, you can get even narrower spread. So in this toy example, the main point here is that if you have more reproducibility in this ground truthing process, that gives you a narrower spread and less uncertainty in your AI's evaluation versus that particular ground truth. So a more reproducible ground truth is usually going to be better. This is a sort of like fairly superficial, toy problem, just to illustrate the point. If you want sort of like a more mathematical treatment of this, we're starting to investigate sort of like a uncertainty-aware kind of evaluation metric. This just went up, I think, last night, and so you can check this out on arXiv.
So in this example, we are taking 10 patients, right?
Yes, in the toy example, there was 10 patients. Mostly also just to have it fit in one figure so we could illustrate a point more easily.
Okay, sure.
Okay, so now most of what we talked about so far involves getting people to label the same thing that a model is seeing. Oftentimes, though, it's very valuable to have information beyond what the model is seeing, whether that's an image, text, or something else. And so it's let's say in the dermatology or radiology space, that often ends up being the biopsy result. And in some other sort of like settings, that ends up being clinical outcomes that you have where you have to follow the patient for a longer time to figure out. So what are some examples of that? Here's one example where we are taking the fundus photo, which is the back of the eye, as input, and this is a photograph, so a color photograph. But the label is coming from an OCT, and this is a 3D imaging technology looking at the fovea. And so using this 3D imaging technology, we can get a label that is higher fidelity than using just a 2D input image. And what we found in this study was that if we do that, and because this is much closer to the gold standard for treatment purposes, when we do that, we get actually quite a significant improvement in performance versus if we had trained using labels where people are just labeling this 2D photograph. And so that's an improvement from versus these 2 colors over here. Here's another example where instead of looking at training using labels of people labeling fundus photographs, we use labels based on what happened to the patient over time. And in this case, this was outcome at a particular time interval. In this study, this was over, I think we trained using 1-year outcomes, and we were looking at the outcomes of the patients stratified by what the model predicts over time. So what we see is that the rate curve, which is high risk model prediction, actually progresses much faster. So they have a worse outcome in this particular problem than those in the green or blue categories. And we've done this quite a bit, in mammography, pathology, ophthalmology, as well as radiology. In some cases, though, within the same study, what we may actually do is to mix and match, meaning that not all of the data sets we're working with, even the test data sets, are using the same set of labels. And so in this particular study, what we then did was to say, hey, can we mix and match and get data sets that are larger, that have lower fidelity labels, for example, from billing codes, and then data sets that are smaller, where there's much higher fidelity labels, for example, from specialists looking at all of the clinical data available. And so when we do this, our objective is not really to say that all of these data sets are comparable, but our objective is to try and see if we can evaluate the model against different ground truth and to see that it is robust, even if the ground truth was different. And in this particular study, we did see that the model performance was good, independent of what ground truth was available in which data set. So beyond evaluation, and tuning, another thing that's important is how the training is done. And so one thing, I think this was a few weeks ago, my colleague Vivek actually gave a talk at MedAI around foundation models, and this was covering the Remedis work. So I won't go into too much detail here, but you can refer to the talk from a while back for that. But just very briefly, in terms of the training, the way that this is done nowadays is, well, very traditionally, the way the training was done was to use kind of like transfer learning in a very fairly simple way, where the model is initially, trained using natural images, so cats, dogs, cars, buildings, planes, and such, and taking that model that has never seen medical images before, we take that and we directly translate that and use that to initialize a model that we are training directly, on, let's say, chest X-rays or something else. Now, more recently, what people have been doing is to try and figure out, can we leverage the fact that sometimes we do have larger data sets of unlabeled medical examples or examples with noisy labels, use that to do a second stage of pre-training before we then apply that, that model to initialize the final supervised training. So how do we do that? Well, there are many variants of this, but some variants involve contrastive learning. And some of the contrastive learning approaches involve sort of like self-supervised contrastive learning. Here's one example where the way it works is you have one example and you take crops from the example, and those are supposed to be the same label because it came from the same image. You take a second example, and because it's a different image, likely it is possibly a different label. And we take crops from that, those two crops should be different than the initial crops you got from the first example. And so that's a self-supervised, one kind of self-supervised contrastive loss. Another way that this is done is to, if you're able to bake in some amount of information that you have, some prior about each image. So for example, if you're looking at chest X-ray reports, sometimes reports will say something like, this is normal. You can bake in that kind of noisy label that is normal or abnormal and use that information in this as well. And so one of those techniques is supervised contrastive loss. And the way this works is to say that, hey, let's say you have categories A and B, and these are noisy labels, and you can take category A crops and use the loss function to tell the model to map it to a more similar space than any examples from category B. And by doing that, you're actually forcing the model to learn better representations by giving it some notion of what is going on within these data. And when you do that, you can then take that and pre-initialize the model for the actual task you're interested in, the supervised loss, and then evaluate it on different data sets. And in this case, the evaluations include both in-distribution evaluation and out-of-distribution evaluation, for example, a different institution. And across multiple tasks, what we saw was that when we do this second step here, it actually substantially helps the amount of data that is needed to achieve good performance. So here are some examples where if you're comparing the blue versus the orange curve, where if you were to do this second step, you actually get much better performance and with respect to the amount of data. And what that translates to directly is both the amount of data required as well as the amount of labeling that's required. And if you're talking about labeling cost, then that actually can save you quite a bit. So this first part of the talk, this part of the talk, one of the take-home points is really, it's not just about the volume of the data, but also the quality of the labels, the kind of data you're using to train and determine the labels, and how do you use it? How do you do the actual training there? This next part here, I want to talk about briefly what happens when you actually have a model and you are thinking about actually using it in practice. How do you take a model and change it into a product? And so here is a vertical timeline. And so in 2016 and 18, this was when we did some of the initial work that you saw earlier in the adjudication piece, so the JAMA paper and the ophthalmology paper, where we did some retrospective evaluation comparing the model performance to ground truth determined by specialists. After that work, we actually spent quite a bit of time working with our partners in Thailand and India, getting additional prospective data and doing additional validation there, just to make sure that we are actually working, the model is generalizing to data, not just the data that we had doing model development, but also data that was more freshly collected. But all of this evaluation here is basically in silico. There was some data that was collected, and we took the data, labeled them, and tried to see what the model performance was. Turns out that was not sufficient, because in the real world, it's not about data points and examples. In the real world, you have stuff happening, you have people standing in line, you have a real workflow that you have to try and integrate with. One thing that we did before we moved to the next step was to do a lot of workflow analysis. And so this is a sketch of a workflow. It looks complicated, but that's kind of the point. What is happening here is this is a sketch of what happens when a patient comes in for a diabetic eye disease screening. So basically every single touch point, who they talk to, whether it's the nurse, the doctor, the ophthalmologist, who they talk to, what happens, what devices are changing hands, where that is happening, all of that is being sketched out. And the purpose of sketching this out is really to understand the workflow, understand if you then add AI to this workflow, which parts of this actually need to change. And the more you can do this in detail with every single site that you're working with, the higher chance you have of actually having things work out, because then you can stay ahead of any issues, such as, for example, in one of the sites that we work with, we found that one of their barriers was that they were taking a photo in a particular room on a particular computer that did not have internet access. So if we were to just tell them, hey, just upload the photo to our API and you'll get back a result, to them, what that actually means is you take a photo, you transfer the photo to a thumb drive, you run with a thumb drive to a different room with internet access, upload it there, and then you reverse the process just to get the results back to the patient. They're not really going to do that for every single patient. And so what you really need to do here is to really figure out what the workflow is and how do you solve for these like operational challenges on the ground. Now, by resolving a lot of these challenges with many individual sites, we worked with our partners in Thailand to conduct a nationwide prospective study across 9 sites and 7,000 patients. And we got really good results here in terms of the model performance. But this was done actually live, meaning the patients were actually getting the AI results live there in person, such that it could be used to help determine whether they needed to see an eye specialist or not. So this second part was much shorter, but the main point here was that beyond getting an accurate model, to get a useful product, you really needed to consider the human factors involved. You needed to understand how do you make this useful for people and pull it all together into an actual product. Now this last part, yeah.
I just had a quick question slash like picking your thoughts about it. I mean, it's super cool that you like were able to deploy this in like a nationwide study, especially in a different environment where the AI model was probably trained on. So I was curious, apart from the operational challenges, did you like have to do anything to make the model a little more generalizable? Like were data qualities like maybe like hardware like differences or maybe just the population like class imbalances and all of that? So was there anything that you needed to do in those aspects as well, apart from like of course like taking care of the operational stuff to include?
Yeah, that's a good question. So at the point that the study was being conducted, the model was actually already CE marked. And so the version that was used for the study was the CE marked version of the algorithm, the most recent version, at each point that the patient had come in. In terms of your question around what we did to get to that point and get it to generalize, I think that initially the model was actually trained on a fairly diverse cohort from the US, as well as validated on data from India and France. That's the Messidor data set. And so we actually, I don't think we specifically trained on data from Thailand for this study, but we did do some validation before we took the hop to the prospective study piece.
Got it. And were there is there a protocol for if people are in doubt about the AI's like results? Is there like a protocol that you had to kind of devise to kind of get human in the loop or like things like that?
Yeah, that's a great question. So this is about essentially how do we handle patient safety, because we were actually using it prospectively. And in this particular case, what was happening was because we had done a fairly large retrospective evaluation in the same program, they gave us confidence that it was actually working pretty well. And so the way we were then, additionally adding another layer of patient safety here was that, in person, when they were getting the results from the AI, they used that to make a decision. But within a certain amount of time, a retina specialist was overreading every single image. And if the overread actually disagreed and said, hey, there might be something in this image that we needed to take care of, then the nurses would be contacted to go get in touch with the patient and tell them, actually, can you please come back in just for safety reasons, because we think there might be a good reason for you to come back. That actually happened pretty rarely in this particular study. I don't have the numbers off the top of my head, but I believe that's in the paper. But that's what we did in this case for safety. And with time, you would imagine that these things will slowly start. This was for a study setting, right? But with time, you would imagine that you would have greater and greater confidence that you wouldn't need to do this for every single patient, because if you did, it would kind of defeat the purpose of having the AI read in the first place.
Got it. Okay, thanks.
Yep. Okay, so I think that was about usability and creating a better product after you have a good model. The last part here is, if you have a product, does that mean that you will get clinical impact? And really what this means is, how do you get the system to actually accept that this product is reasonable, is good for the patients, and is something that people should pay for, and that's something that's self-sustaining. And a lot of this really revolves around modeling what happens in the aggregate at the system level. So here's one example of a study. This was not our study. This was from a team in Singapore. And what they did here was they compared panel A is their regular workflow. In this workflow, they had human graders grading images that indicates whether the images contained a disease that's referable. And there's a second grader that's checking it before they do the final determination of whether to refer to the eye center. They imagined a fully autonomous process here where there was just one AI grading everything into referable versus not, and that determined the refer decision, as well as a hybrid model where there was an AI model doing this initial, essentially triaging, and then a second grader that's doing a secondary check before the final refer decision is being made. Now, one thing they found when they compared these three approaches was something slightly paradoxical, in that they found that the cost of this fully autonomous process was actually higher than that of this hybrid process. And it turns out that the reason for that being the case in their study was that their AI actually was referring quite a number of patients. And so if you would refer everyone that AI thought was, had disease, then that ends up giving you a pretty high referral rate, and that drives up costs because referral to the eye specialist is pretty costly for the system. In this hybrid system, what they realized was that by having this manual check by the secondary graders, this manual check can help remove images that people might not have referred, and have them be rescreened in a year. So if something was actually up, they would be seen in a year anyway. And so in this case, they reduce cost for them by quite a bit without really harming the outcomes. So this was a study in Singapore. We've also worked with our partners in Thailand to take a look at what was happening for their system. So they plugged in numbers wherever available for their own system in terms of costs and such, and if not available, comparable numbers from other comparable countries. They were comparing essentially two possible methods. One was screening using their current approach, using human graders. Another approach was screening using the AI, so just fully autonomous versus fully human. And what they realized was that the AI was actually better at catching referable disease. And as more people are caught, more people are treated. And the cost of the treatment is actually quite high. And so what was happening was that if you use the AI, it was achieving its goals by detecting more disease. But because you're treating a disease, that actually increases costs for the system as opposed to lowering costs. So in their case, if you just compare what is the cost of the treatment, you're actually paying strictly more for treating more people that were actually correctly caught by the AI. Now, this is a little bit of a paradox because you're trying to do the right thing and catching more people with disease, but once you treat them, you're actually incurring more costs for the system. But then they realize that actually this is not the full story. To capture the full story, you have to figure out, well, you can't just put a dollar amount on catching disease and saying that treating more people is bad. What does the society actually, what happens to society if you're able to treat more people? And so then they started incorporating the cost of treatment and also accounting for societal costs of bilateral blindness when someone goes blind in both eyes, And when they incorporated that, they realized that overall, once you incorporate a societal cost, it was actually much better, as you might expect, to catch more people and correctly treat them than to rely on, lower performance, sort of like human graders. So, there was a very brief third part to that, but, the takeaway here is that to get a good product that is making clinical impact, you really have to look at the overall system and then figure out how do the patients, clinicians, and the system interact, like where are the dollars flowing, and how do you get it to such a point where it makes sense for a system to take up a product that actually helps patients. So a brief recap of kind of like the first part of this is that, it's good to get more data, but you really have to use it right to get the optimal benefit. It's good to have accurate model, but to get a useful product, you have to consider a bunch of human factors and make it usable by the people. And lastly, if you have a good product, to actually make clinical impact, you have to make sure that the system is overall incentivized to use it by doing the right health economics analysis here. And then we have a paper discussing quite a bit of this work as a viewpoint at Nature Medicine published recently. So I'm going to switch gears a little bit now to touch on a different topic. And this topic is really about what can you do with AI that goes beyond predictions. Most of what we talked today was really about how to use deep learning in such a way to do something that people are trying to do right now in an existing workflow, and to use that to increase accessibility to healthcare. So I'm going to go through 3 examples in this general space where we're trying to go beyond predictions. Although most of these actually starts with predictions. So here's one example in pathology where this was a colorectal cancer problem where the input are images of resections from colon cancer, and the objective is to determine if they're gonna what kind of prognosis the case will have. So we trained a model using weakly supervised learning where it was taking little crops from these large images, and it was trained to predict the outcome. And then we verified that the outcomes that it was predicting actually did correlate with the person's actual outcomes in retrospective studies. So that was a good thing. The model was actually predicting prognosis well. Now, the problem was that this model, if you were to try and use this in an autonomous fashion, it doesn't actually tell you like what is it about these images that are actually predictive of the prognosis. It's really hard to understand. And we had quite a bit of trouble diving into the details of this, especially because these images were very large. So we couldn't do a lot of the techniques that people were doing, including saliency and such, and it was very, very hard to do. So the way we tackled this was we used an approach to take each patch that goes through the prognostic model, and then we clustered these patches, and then for each cluster, we computed the average score that this prognostic model was giving. When we did that, and we arranged the clusters such that the highest ranked clusters based on poor prognosis actually, was at the top, we saw that one of the clusters actually jumped out in terms of the prognosis. And this turned out to be a cluster we dubbed the tumor adipose feature, meaning that there were little clusters of tumor cells interspersed with this white stuff, which was fat tissue. And at this point, we realized that, hey, this was something that's actually fairly distinctive. We did a quick study where we got both experts, so pathologists, and non-experts, so folks like myself, engineers, and other researchers, to look at pairs of examples where one pair is from this cluster, and another element of the pair was from some other cluster. And we actually found that both experts and non-experts could determine whether a particular image patch belonged to this TAF feature or not with more than 90% accuracy. And this was including non-experts. So we realized that this was actually a visually very, very distinctive feature that was jumping out in this particular analysis. So then what we did then next was we worked with some pathologists in a different team. So this was work originally done with a team in Graz, and this was work done with a team in Milan. And this team in Milan actually went into their data set and they used regular microscopes. So without even scanning the slides, they used regular microscopes, and their pathologists reviewed these cases for the amount of TAF that was on each case. And from the human reviewed amount of TAF, we found that the human scoring of TAF actually also correlated with patient prognosis and remained significant after adjusting for known things like TNM staging and other things. So what we did essentially in this line of work was that we actually had a model that was doing prognosis and was trained in a weakly supervised fashion. We found out which clusters tended to be actually correlated with the model predictions. And then we had people that could then understand what the model was trying to predict, scored for that feature. And then we found that a human scoring of a machine learning feature actually correlated with prognosis. So that was one example. In a second example, what we did, this is something that you saw, I think, earlier in the slide, where this was a problem where we were taking as input a 2D modality, and the model was trained to predict labels from a 3D modality. Now, when the model does this, we have a few questions. Is the model using the same features that humans are using when humans use the 2D modality to do the prediction? And in this case, these are heart exits or these little yellow spots here near the fovea. Is the model using that as well, or is it using something else? Like, why does the model perform better? So the way we approached this problem was we used a cyclogram-based approach, where essentially the way the cyclogram works is that it takes the input examples from category A, and the cyclogram model is trained to take a category A example and transform that into category B. You have a second model that's doing the opposite, transforming a B into A. Now, when you do this, what you can do is apply that to examples and try and see what is the model starting to change. And so here's what we did. And on the left here, these are from examples with disease to examples without disease. And what we found was that consistently what the model tended to do was that it took examples with disease with this yellow spots and started to remove those yellow spots. And we saw that pretty consistently. And on the right side, these are examples where there's no disease. And when we asked the model to transform it into those with disease, it started to add some of these yellow spots. So yes, the model does seem to learn that same correlation where these yellow spots are correlated with disease. But at the same time, we also found that the fovea was actually brightening when in some of these transformations. So then what we did here was we said, okay, so the model seems to be doing this. Let's engineer features to reflect the fovea brightening and other things that we think the model is looking at. And then we engineered those features to extract those features and added it to a hand-engineered model. And we found that that new engineered model actually improves in performance, validating that what we think the model is looking at is actually predictive of this DME label from a 3D modality. So this is the second example. Now, the third example is a little bit more complicated. So let me go into a little bit of what the technique looks like. In this third example, it's also a GAN-based approach, but this, instead of using cycloGAN, it does a StyleGAN-like approach. So what's happening in StyleGAN is, as opposed to saying change A into B, which is this counterfactual sort of like generation approach, it says, hey, when you do this generation, I'm going to map the encoded embeddings that you have into a particular space. And in that space, I'm able to change each individual attribute in that space individually. And so when you are able to do that, it turns out that some of these attributes that you're changing actually turns out to be human interpretable. So here's an example from a cat-dog detector where changing individual attributes actually changes things about the ears, the mouth, and the eyes of this cat. And that changes these properties that make the model think this is more cat-like versus more dog-like. So essentially, we took this particular technique and then we applied it into some of the other predictions we were working on. So here's one example where we were working with external eye predictions. So these are photos of the outside of the eye, not the inside. And this is a positive control because what we were predicting in this particular model, where we're taking examples here and trying to predict if there was cataract. Now, cataract is when there's media opacity in the lens. So when there is cataract, you actually expect that this part becomes a bit more cloudy. And that's exactly what we saw when we used this StyleGAN-like approach. Now, what was interesting is when we started looking at some predictions that were more novel that people were not doing or people did not know how to do. One example was the A1C approach, A1C prediction. And A1C is a reflection of the amount of blood sugar. And when it's high, it's more likely that someone has diabetes. What we found, interestingly, was that we looked at one of the features that was strongly predictive of the model thinking that the eyes belong to a patient with higher A1C. And it turns out that the model is actually making this eyelid margin here more pale. Now, this was a little bit unusual. And so when we dug into the literature, what we found was that when people have diabetes, they're much more likely to have something called meibomian gland disease. And these are glands underneath this eyelid section here that plays a part in tear production. And the process of diabetes tends to interfere with those glands. And then this is maybe potentially what we're seeing here. So this is what we think is, is consistent with some knowledge in the literature, but that reflects knowledge that people are not using right now. It's not all good stuff that we were seeing though. So here's one that's a little bit more interesting. What we saw here was that, to predict higher A1C levels, the model actually thought that there was the presence of this ARCUS feature. And ARCUS feature is this white thing here around at the edge of this iris here. And this feature actually is correlated with age. And what we saw here, the fact that this feature was appearing was actually very, very confusing. And it turns out, and we think what's happening here is that this is essentially an artifact of the data set. And what I mean by that is that this data set comes from people who are going for diabetic eye disease screening. And so if they do not have diabetic eye disease screening, they keep coming back every year. And once they do have diabetic eye disease and it's detected, in the screening program, what should happen is that they should get a referral to eye care, specialist eye care, and they should get referred essentially out of the program. So what you have is this statistical bias where the older people are in the program, the more likely that they have not yet had diabetic eye disease, and this reverse bias is what we were seeing in this particular feature. So this is, we think, not something that's about the physiology, but because of the statistical properties of the dataset. So let's recap a little bit the three kind of like types of examples that we saw and how it fits into the paradigm that we've been talking about earlier in the talk. So in traditional machine learning, we are really looking at raw data and human knowledge and combining those in some way to engineer features and using data to then train the feature engineered model to do some prediction task. In the deep learning paradigm, what we're really doing is really trying to take raw data and labels and getting the model to learn what the features are. And so skipping some of these steps. What we think some of the work that we're doing now represents, and we hope to see more in this area, is that if we don't stop purely at the model's learning from raw data component, if we add interpretability and we show that what we interpret out of it is actually reproducible knowledge, then we are actually adding to human knowledge as we do these prediction problems. And so what we really want to see is more work in the space of learning from deep learning, in addition to all the impactful healthcare work, but also to then drive and add more to the pool of human knowledge. And with that, I conclude my talk. Thank you for your attention. I'm open to more questions.
Awesome. Thanks so much, Yoon. I think this was amazing work and very exciting to see all the interpretability work as well. Yeah, so before we get started with questions, maybe we can give a round of virtual applause for our speaker today, and then we'll open the floor for questions. So maybe we can, just to make it easier, if people have a question, just raise your hand and then we'll call on you, and then we can get started with that. Oh yeah, Amara, go for it.
Yeah, thank you very much. It's a very interesting talk. If you can just go back one slide, I think it's your last slide when you're talking about this basically reverse pipeline where model building is then followed by interpretability and human knowledge. As you've mentioned in some of the examples, I mean, some of the interpretability examples, they make sense, like they're clinically useful, but then sometimes it's just bias, right? The way you were showing that survivorship bias. Any thoughts on, changing the forward process as well? Is there any way you think to make the model focus on more clinically relevant stuff rather than this kind of data bias or any other type of bias? Do you think have you thought about changing this, changing the model development the other way around as well?
Yeah, so that's a good question. How do we tackle and control what the model is learning? And because when we provide it with a target label to predict, that's an underspecified problem. We're not saying how to do it, we're just saying I want to accomplish this, right? And that's I think it's a common theme across many kind of like machine learning problems, in this space where we have much less control over how. So I think we've done a little bit of work in this space. One example is not quite what we're asking, but it's kind of related, where we actually did feature selection in such a way that, sorry, let me backtrack a little bit. So in some of the problems that we're doing in the cancer space, we would often try and make a prediction, and then we take the model and we say, oh, good, so it's now able to do this prediction for prognosis or for cancer presence or something. And then we say, what are people actually currently doing to make this prediction, which can be TNM staging, which can be some mutational status and other things. And then we do an adjusted analysis to say, okay, does the model add on to this known features already? Right. So that's one common pattern where we post hoc try and assess if the model has learned anything new. And often we do find that it has learned something new, but this is a post hoc things. And so if it didn't learn something new, like, what would you do then? What we tried to do in one work in sort of like this space was to say, well, how about we generate a bunch of features, and then we do feature selection with the existing features already in that pool of features. So that way, when it's actually selecting features, it should only select stuff that's most helpful when added to the pool of stuff that's already in there. Right? And so by doing that, we actually showed that it was actually selectively trying to get new stuff, as opposed to stuff that correlates very highly with stuff that's already being used in production. So I think that's one general route that one can try and do things by, where if you do have the ability to pre-generate things that are already essentially used clinically, you can then try and see if the model can learn stuff that's new on top of that, as opposed to just reproducing stuff that people already know. So that's one route to learn new knowledge. Your question, I think, also focuses a little bit more on how to avoid it learning stuff that you don't want it to learn. I think that's much harder, because the space of what is already known is finite. The space of what it shouldn't maybe do is potentially infinite. And so I think that's a harder problem. Some things you can try and do is to and there are many ways to do this, where there's some ways where you can backpropagate losses to try and say, hey, you seem to be learning this. I'm going to give you a negative gradient to say don't learn this thing, right? Where you penalize the model for learning certain things that you don't want it to. Another way you can do it is if you know there's one specific sort of category of problems that you don't want it to sort of learn that bias for, you can then essentially sample the data set in such a way that you break that bias. So that's another way to do it. And there's many more techniques in that space, but I think it's very hard to do to solve the general problem of saying don't learn anything I don't want you to learn, because it's hard to define what that means. But if you know that there's a small set of things that don't make sense to learn, then you can try and factor that into the model learning process.
Thank you. And I think like some of what you don't want the model to learn, maybe it becomes apparent only after training a model. For example, the survivorship bias might not be known already, that, oh, model will learn that and this is not useful. So once you have a model, maybe a little bit of investigation into interpretability, and you maybe help you at least stop that model from learning it further. Thank you very much.
Yeah, definitely. And I can give another example that's in the paper. This is a slide after. Didn't want to crowd with too many. Oh, actually, I don't have it here. So I'll just try to verbally describe this somehow. So in this example, it was from this set of work, except that instead of predicting A1C elevation, we were predicting hemoglobin levels. And so then what we saw was the model learned in association between essentially eyeliner presence and hemoglobin levels. And part of this association is present, because women of a certain age group tend to be more likely to wear eyeliners, and females tend to have a lower hemoglobin level than males. So that's just a known association. And so this association does exist in the data, but it is something that a model ended up picking up on. I don't think it was a top feature that by any means, but it was something that was an association in a data set. It's not something that I think we would have a priori, to your point, expected and say, hey, don't learn this, right? But we had to sort of go back and extract that and then understand, okay, now how do we solve for this? Like, well, first of all, is this something that we want? Probably not. And how do we solve for that?
That's very interesting. Thank you.
I actually had I wanted to piggyback on this discussion. I think it's a great one point that Amara brought up. So like I find that contrastive learning methods are in general like very robust, like they provide like good sense of generalizability that other methods don't. But for the kinds of things that you are highlighting here, like for instance, like maybe the eyelid margin color or like some of the other examples, it kind of feels like some of the transformations that we use in contrastive learning, like the augmentations that we kind of want the model to be robust to, they might be suppressing the things that the model is actually picking up on. Like for instance, I can imagine if you add a little bit of blurring or like maybe you do some color transformations, this signal is actually going to be lost. So which means that we are actively training the model to kind of be invariant to these features. Is there a good compromise, or like at least I'm a little biased because I study augmentations and say we need domain specific augmentations to kind of go to the downstream task. But I wanted to hear your thoughts on how, like at least for this problem or in other problems that you face, how do you inject domain knowledge to make sure that we're not, suppressing these things while training itself?
Yeah, that's a good question. So I think it depends on, so contrastive learning is just sort of like one way to do, self-supervised learning to get better representational learning. I think sort of like I will work backwards and try and figure out like what the objective of that representation is for. And then whenever possible, customize or engineer the sets of augmentations and maybe even the way you're doing self-supervised learning or pre-training or anything based on that final goal that you have in mind, right? So if the goal is something where, let's say, that it's, so maybe here's an example, right? Let's say the goal is to do diabetic eye disease detection using a new camera that's sort of like, that you don't really have as much data for. Well, you don't have much label data for, but you have some amount of unlabeled data. Maybe what you want to do is try and figure out, is there a way I can, bootstrap and produce some noisy labels for this, not labels that I fully trust, but something noisy, and use that to do some kind of, it can be active learning, but it can also be sort of like self-supervised learning or, or some kind of semi-supervised learning as well, right? And as you do that, because it's a space that you're sort of like, you have a sense of what you're trying to get out of it at the very end. So for example, if you know that it's diabetic eye disease and you know that, let's say, the microaneurysms that you want to detect are, let's say, 2 pixels across, right? As you know that, you would not want to then use, let's say, blurring augmentations that then essentially can smoosh out any of these, small lesions. But you would rather focus on stuff that, let's say, about some other kinds of like overall color hue, sort of like saturation changes that you think are sort of like somewhat realistic. You might inspect the data and try to understand what kinds of stuff tends to happen in the data set. For example, does the new camera tend to distort things in a specific way? Can you add distortion and shearing and other kinds of transformations that are easily engineered, but also relevant to this particular problem? So I think it's really about tackling this in a very targeted way whenever you can. Yeah, so unfortunately, I don't know that there's a sort of like a more general way to do it, but definitely worth investigating based on the problem.
Yeah, I was just thinking about like when you really want to do these large scale foundation models where you do not know a priori where you're going to use them for. So so you do have to rely on like, going as broad as possible and then kind of honing in. So you might have to relearn some of the things that you became invariant to in like the pre-training stage. So yeah, thank you.
Yeah, definitely.
I know we are slightly over time, so it's I guess if are there any final questions that maybe like you want to ask Yoon, or if not, we'll end the session now. I'll just give like a small pause in case like somebody has some very quick question. Okay, so if not, thank you so much, Yoon, again for presenting all this work, and it's really great to see like the models that you're building is actually going much closer to like making really positive clinical impact. So that's pretty heartening to see. And we'll put up this talk on YouTube later today. And if people have more questions, we'll put them in touch with you. So thank you all for joining, and thanks again for presenting today.
Awesome. Thank you for the invitation and for joining us during this lunch hour.
Absolutely. And we'll see you all next week at our regular time, 1 p.m. So.
Sounds good. Thank you, everyone.